Hello, and welcome to SQL for Data Science. The demand for data scientists is high, boasting a median base salary of $110,000 and job satisfaction score of 4.4 out of 5. It's no wonder that it's the top spot on Glassdoor's Best Jobs in America. Glassdoor analyzed data from data scientist job postings on Glassdoor and found that SQL is listed as one of the top 3 skills for a data scientist. Before you step into the field of data science, it is vitally important that you set yourself apart by mastering the foundations of this field. One of the foundational skills that you will require is SQL. SQL is a powerful language that's used for communicating with databases. Every application that manipulates any kind of data needs to store that data somewhere, whether it's big data or just a table with a few simple rows for government or a small startup, or a big database that spans over multiple servers or a mobile phone that runs its own small database. Here are some of the advantages of learning SQL for someone interested in data science. SQL will boost your professional profile as a data scientist, as it is one of the most sought-after skills by hiring employers. Learning SQL will give you a good understanding of relational databases. Tapping into all this information requires being able to communicate with the databases that store the data. Even if you work with reporting tools that generate SQL queries for you, it may be useful to write your own SQL statements so that you need not wait for other team members to create SQL statements for you. In this course, you will learn the basics of both the SQL language and relational databases. The course includes interesting quizzes and hands-on lab assignments, where you can get experience working with databases. In the first few modules, you work directly with the database and develop a working knowledge of SQL. Then, you will connect to a database and run SQL queries like a data scientist typically would, where you will use Python and Jupyter notebooks to connect to relational databases to access and analyze data. There is also an assignment included towards the end of the course, where you will get an opportunity to apply the concepts that you learned. So let's get started with SQL for Data Science. Hello, and welcome to SQL for Data Science. First, we will talk a little bit about what you'll learn in this course. This course teaches you the basics of the SQL language and the relational database model. There will be some lab exercises, and at the end of each section, there are a few review questions, and at the end, there is a final exam. By the end of this course, you will be able to discuss SQL basics and explain various aspects of the relational database model. In this video, we will learn about SQL and relational databases. By the end of this video, you will be able to describe SQL, data, database, a relational database, and list 5 basic SQL commands. But wait, what is SQL and what is a relational database? What is SQL? SQL is a language used for relational databases to query or get data out of a database. SQL is also referred to as SQL, and is short for its original name, Structured English Query Language. So SQL is a language used for a database to query data. But what is data? And what is a database? Data is a collection of facts in the form of words, numbers, or even pictures. Data is one of the most critical assets of any business. It is used and collected practically everywhere. Your bank stores data about you, your name, address, phone number, account numbers, etc. Your credit card company and your PayPal accounts also store data about you. Data is important, so it needs to be secure, and it needs to be stored and accessed quickly. The answer is a database. So, what is a database? Databases are everywhere and used every day, but they are largely taken for granted. A database is a repository of data. It is a program that stores data. A database also provides the functionality for adding, modifying, and querying that data. There are different kinds of databases of different requirements. The data can be stored in various forms. When data is stored in tabular form, the data is organized in tables, like in a spreadsheet, which is columns and rows. That's a relational database. The columns contain properties about the item, such as last name, first name, email address, city. A table is a collection of related things, like a list of employees or a list of book authors. In a relational database, you can form relationships between tables. So a database is a repository of data. A set of software tools for the data in the database is called a database management system, or DBMS for short. The terms database, database server, database system, data server, and database management systems are often used interchangeably. For relational databases, it's called a Relational Database Management System, or RDBMS. RDBMS is a set of software tools that controls the data, such as access, organization, and storage. An RDBMS serves as the backbone of applications in many industries, including banking, transportation, health, and so on. Examples of relational database management systems are MySQL, Oracle Database, DB2 Warehouse, and DB2 on Cloud. For the majority of people using a database, there are 5 simple commands to create a table, insert data to populate the table, select data from the table, update data in the table, delete data from the table. So those are the building blocks for SQL for data science. You can now describe what is SQL, what is data, what is a database, and what is a relational database. You know that RDBMS stands for Relational Database Management System. And you can list 5 basic SQL commands to create a table, insert data to populate the table, select data from the table, update data in the table, and delete data from the table. Thanks for watching this video. Hello, and welcome to Retrieving Data with the Select statement. In this video, we will learn about retrieving data from a relational database table by selecting columns of a table. At the end of this lesson, you will be able to retrieve data from a relational database table, define the use of a predicate, identify the syntax of the select statement using the where clause, and list the comparison operators supported by a relational database management system. The main purpose of a database management system is not just to store the data, but also facilitate retrieval of the data. So, after creating a relational database table and inserting data into the table, we want to see the data. To see the data, we use the select statement. The select statement is a data manipulation language statement. Data manipulation language statements, or DML statements, are used to read and modify data. The select statement is called a query, and the output we get from executing this query is called a result set, or a result table. In its simplest form, a select statement is select star from table name. Based on the book entity example, we would create the table using the entity name book and the entity attributes as the columns of the table. The data would be added to the book table by adding rows to the table using the insert statement. In the book entity example, select star from book gives a result set of 4 rows. All the data rows for all columns in the table book are displayed. In addition, you can also retrieve all the rows for all columns by specifying the column names individually in the select statement. You don't always have to retrieve all the columns in a table. You can retrieve just a subset of columns. If you want, you can retrieve just 2 columns from the table book, for example, book_ID and title. In this case, the select statement is select book_ID, title from book. In this case, only the 2 columns display for each of the 4 rows. Also notice that the order of the columns displayed always matches the order in the select statement. However, what if we want to know the title of the book whose book_ID is B1? Relational operation helps us in restricting the result set by allowing us to use the clause where. The where clause always requires a predicate. A predicate is a condition that evaluates to true, false, or unknown. Predicates are used in the search condition of the where clause. So, if we need to know the title of the book whose book_ID is B1, we use the where clause with the predicate book_ID equals B1. Select book_ID, title from book, where book_ID equals B1. Notice that the result set is now restricted to just one row whose condition evaluates to true. The previous example used the comparison operator equal to in the where clause. There are other comparison operators supported by a relational database management system: equal to, greater than, less than, greater than or equal to, less than or equal to, and not equal to. Now you can retrieve data and select columns from a relational database table, define the use of a predicate, identify the syntax of the select statement using the where clause, and list the comparison operators supported by a relational database management system. Thanks for watching this video.
Hello and welcome. In this video, we'll briefly present a few useful expressions that are used with select statements. The first one is count. Count is a built-in database function that retrieves the number of rows that match the query criteria. For example, get the total number of rows in a given table. Select count star from table name. Let's say you create a table called metals, which has a column called country, and you want to retrieve the number of rows where the medal recipient is from Canada. You can issue a query like this. Select count country from metals where country equals Canada. The second expression is distinct. Distinct is used to remove duplicate values from a result set. Example, to retrieve unique values in a column. Select distinct column name from table name. In the metals table mentioned earlier, a country may have received a gold medal multiple times. Example, retrieve the list of unique countries that received gold medals, that is, removing all duplicate values of the same country. Select distinct country from metals where medal type equals gold. The third expression is limit. Limit is used for restricting the number of rows retrieved from the database. Example, retrieve just the first 10 rows in a table. Select star from table name, limit 10. This can be very useful to examine the result set by looking at just a few rows instead of retrieving the entire result set, which may be very large. Example, retrieve just a few rows in the metals table for a particular year. Select star from metals where year equals 2018, limit 5. In this video, we looked at some useful expressions that are used with select statements, namely the count, distinct, and limit built-in functions. Thanks for watching this video.
Hello, and welcome to the insert statement. In this video, we will learn about populating a relational database table. At the end of this video, you will be able to identify the syntax of the insert statement and explain two methods to add rows to a table. After a table is created, the table needs to be populated with data. To insert data into a table, we use the insert statement. The insert statement is used to add new rows to a table. The insert statement is one of the data manipulation language statements. Data manipulation language statements, or DML statements, are used to read and modify data. Based on the author entity example, we created the table using the entity name, author, and the entity attributes as the columns of the table. Now we will add the data to the author table by adding rows to the table. To add the data to the author table, we use the insert statement. The syntax of the insert statement looks like this. Insert into table name, column name, values. In this statement, table name identifies the table. The column name list identifies each column in the table, and the values clause specifies the data values to be added to the columns in the table. To add a row with the data for Raoul Chong, we insert a row with an author underscore ID of A1, the last name as Chong, the first name as Raoul, the email as rfc@ibm.com, the city as Toronto, and the country as CA for Canada. The author table has 6 columns, so the insert statement lists the 6 column names, separated by commas, followed by a value for each of the columns, also separated by commas. It is important that the number of values provided in the values clause is equal to the number of column names specified in the column name list. This ensures that each column has a value. Tables do not need to be populated one row at a time. Multiple rows can be inserted by specifying each row in the values clause. In the values clause, each row is separated by a comma. For example, in this insert statement, we are inserting 2 rows, one for Raul Chong and one for Rav Ahuja. Now you can identify the syntax of the insert statement and explain the 2 methods to add rows to a table, one row at a time or multiple rows. Thanks for watching this video. Hello, and welcome to the update statement and the delete statement. In this video, we will learn about altering and deleting data in a relational database table. At the end of this lesson, you will be able to identify the syntax of the update statement and delete statement, and explain the importance of the where clause in these statements. After a table is created and populated with data, the data in a table can be altered with the update statement. The update statement is one of the data manipulation language, or DML statements. DML statements are used to read and modify data. Based on the author-entity example, we created the table using the entity name author and the entity attributes as the columns of the table. Rows were added to the author table to populate the table. Sometime later, you want to alter the data in the table. To alter or modify the data in the author table, we use the update statement. The syntax of the update statement looks like this: update table name set column name equal to value where condition. In this statement, table name identifies the table. The column name identifies the column value to be changed, as specified in the where condition. Let's look at an example. In this example, you want to update the first name and last name of the author with author_IDA2 from Rav Ahuja to Lakshmi Kata. In this example, to see the update statement in action, we start by selecting all rows from the author table to see the values. To change the first name and last name to Lakshmi Kata, where the author ID is equal to A2, enter the update statement as follows: update author set last name equal to Kata, first name equal to Lakshmi, where author ID is equal to A2. Now to see the result of the update, select all rows again from the author table, and you will see that in row 2 the name changed from Rav Ahuja to Lakshmi Kata. Note that if you do not specify the where clause, all the rows in the table will be updated. In this example, without specifying the where clause, all rows in the table would have changed the first and last names to Lakshmi Kata. Sometime later, there might be a need to remove one or more rows from a table. The rows are removed with the delete statement. The delete statement is one of the data manipulation language statements used to read and modify data. The syntax of the delete statement looks like this: delete from table name, where condition. The rows to be removed are specified in the where condition. Based on the author entity example, we want to delete the rows for author ID A2 and A3. Let's look at an example. Delete from author where author ID in A2, A3. Note that if you do not specify the where clause, all the rows in the table will be removed. Now you can identify the syntax of the update statement and delete statement, and explain the importance of the where clause in these statements. Thanks for watching this video.
Hello and welcome to Database Concepts. In this video, we will learn about different types of models, how we use models to map data to tables, and define relationships between tables. At the end of this lesson, you will be able to explain the advantage of the relational model, explain how the entity name and attributes map to a relational database table, describe the difference between an entity and an attribute, identify some commonly used data types, and describe the function of primary keys. The relational model is the most used data model for databases because this model allows for data independence. Data is stored in a simple data structure, tables. This provides logical data independence, physical data independence, and physical storage independence. An entity relationship data model, or ER data model, is an alternative to a relational data model. Using a simplified library database as an example, this figure shows an entity relationship diagram, or ERD, that represents entities, called tables, and their relationships. In the library example, we have books. A book can be written by one or many authors. The library can have one or many copies of a book. Each copy can be borrowed by only one borrower at a time. An entity relationship model proposes thinking of a database as a collection of entities. Rather than being used as a model on its own, the ER model is used as a tool to design relational databases. In the ER model, entities are objects that exist independently of any other entities in the database. The building blocks of an ER diagram are entities and attributes. An entity can be a noun, person, place, or thing. In an ER diagram, an entity is drawn as a rectangle. Entities have attributes, which are the data elements that characterize the entity. Attributes tell us more about the entity. In an ER diagram, attributes are drawn as ovals. Using a simplified library as an example, the book is an example of an entity. Attributes are certain properties or characteristics of an entity and tell us more about the entity. The entity book has attributes such as book title, the edition of the book, the year the book was written, etc. Attributes are connected to exactly one entity. The entity book becomes a table in the database, and the attributes become the columns in a table. A table is a combination of rows and columns. While mapping, the entity becomes the table. Having said that, the table has not yet taken the form of rows and columns. The attributes get translated into columns in a table, providing the actual table form of rows and columns. Later, we add some data values to each of the columns, which completes the table form. Each attribute stores data values of different formats: characters, numbers, dates, currency, and many more besides. In the book table example, the title is made up of characters. As book titles vary in length, we can set the variable character data type for the title column, varchar. For character columns that do not vary in length, we use character, or char. The edition and year columns would be numeric. The ISBN column would be char because it contains dashes as well as numbers, and so on. Using the book entity mapping as an example, we can create the tables for the remainder of our simplified library example using entity names like author, author list, borrower, loan, and copy. The entity attributes will be the columns of the tables. Each table is assigned a primary key. The primary key of a relational table uniquely identifies each tuple or row in a table, preventing duplication of data and providing a way of defining relationships between tables. Tables can also contain foreign keys, which are primary keys defined in other tables, creating a link between the tables. Now you know that the key advantage of the relational model is logical and physical data independence and storage independence. Entities are independent objects which can have multiple characteristics called attributes. When mapping to a relational database, entities are represented as tables and attributes map to columns. Common data types include characters such as char and varchar, numbers such as integer and decimal, and timestamps including date and time. A primary key uniquely identifies a specific row in a table and prevents duplication of data. Hello and welcome. This video will cover the key concepts around databases in the cloud. In order to learn SQL, you first need to have a database available to practice your SQL queries. An easy way to do so is to create an instance of a database in the cloud and use it to execute your SQL queries. After completing this lesson, you will be able to understand basic concepts related to cloud databases, list a few cloud databases, describe database service instances, as well as demonstrate how to create a service instance on an IBM DB2 on cloud. A cloud database is a database service built and accessed through a cloud platform. It serves many of the same functions as traditional databases with the added flexibility of cloud computing. Some advantages of using cloud databases include ease of use. Users can access cloud databases from virtually anywhere using a vendor's API or web interface, or your own applications, whether on cloud or remote. Scalability. Cloud databases can expand and shrink their storage and compute capacities during runtime to accommodate changing needs and usage demands, so organizations only pay for what they actually use. Disaster recovery. In the event of a natural disaster or equipment failure or power outage, data is kept secure through backups on remote servers on cloud in geographically distributed regions. A few examples of relational databases on cloud include IBM DB2 on cloud, databases for PostgreSQL on IBM Cloud, Oracle Database Cloud Service, Microsoft Azure SQL Database, and Amazon Relational Database Services. These cloud databases can run in the cloud either as a virtual machine, which you can manage, or delivered as a managed service depending on the vendor. The database services can either be single or multi-tenant depending on the service plan. To run a database in cloud, you must first provision an instance of the database service on the cloud platform of your choice. An instance of a database as a service, or DBaaS, provides users with access to database resources in cloud without the need for setting up of the underlying hardware, installing the database software, and administering the database. The database service instance will hold your data in related tables. Once your data is loaded into the database instance, you can connect to the database instance using a web interface or APIs in your applications. Once connected, your application can send SQL queries across to the database instance. The database instance then resolves the SQL statements into operations against the data and objects in the database. Any data retrieved is returned to the application as a result set. Now let's see how a database instance is created for DB2 on cloud. IBM DB2 on cloud is a SQL database provisioned for you in the cloud. You can use DB2 on cloud just as you would use any database software, but without the overhead and expense of hardware, setup, or software installation and maintenance. Now let's see how we can set up a service instance of DB2. Navigate to IBM Cloud Catalog and select the DB2 service. Note there are several variations of the DB2 service, including DB2 Hosted and DB2 Warehouse. For our purposes, we will choose the DB2 service, which comes with a free Lite plan. Select the Lite plan. If need to, change the defaults. You can type a service instance name, choose the region to deploy to, as well as an org and space for the service. Then click Create. You can view the IBM DB2 service that you created by selecting Services from your IBM Cloud dashboard. From this dashboard, you can manage your database instance. For example, you can click on the Open Console button to launch the web console for your database instance. The web console allows you to create tables, load data, explore data in your tables, and issue SQL queries. In order to access your database instance from your applications, you will need the service credentials. For the first time around, you'll need to create a set of new credentials. You can also choose to create multiple sets of credentials for different applications and users. Once a set of service credentials is created, you can view it as a JSON snippet. The credentials include the necessary details to establish a connection to the database and includes the following: a database name and port number, a host name, which is the name of the server on the cloud on which your database instance resides, a username, which is the user ID you'll use to connect along with the password. Note that your username is also the schema name in which your tables will be created by default. Now that you know how to create a database instance on cloud, the next step is to actually go and create one. Thank you for watching this video. Welcome to Types of SQL Statements. At the end of this video, you will be able to distinguish between data definition language statements and data manipulation language statements. SQL statements are used for interacting with entities, that is, tables, attributes, that is, columns, and their tuples, or rows with data values, in relational databases. SQL statements fall into two different categories: data definition language statements and data manipulation language statements. Data definition language, or DDL statements, are used to define, change, or drop database objects such as tables. Common DDL statement types include create, alter, truncate, and drop. Create, which is used for creating tables and defining its columns. Alter is used for altering tables, including adding and dropping columns and modifying their data types. Truncate is used for deleting data in a table, but not the table itself. Drop is used for deleting tables. Data manipulation language, or DML statements, are used to read and modify data in tables. These are also sometimes referred to as CRUD operations, that is, create, read, update, and delete rows in a table. Common DML statement types include insert, select, update, and delete. Insert is used for inserting a row or several rows of data into a table. Select reads or selects row or rows from a table. Update edits row or rows in a table, and delete removes a row or rows of data from a table. Now you know that DDL, or data definition language statements, are used for defining or changing objects in a database, such as tables. And DML, or data manipulation language statements, are used for manipulating or working with data in tables. Thanks for watching this video. Welcome to Create Table Statement. At the end of this video, you will be able to explain how the entity name and attributes are used to create a relational database table. Now let's look at the most common DDL statement, create. The syntax of the create table is shown here. You start with create table, followed by the name of the table you want to create. Then enclose the rest of the statement inside a pair of parentheses or round brackets. Each row inside the parentheses specifies the name of a column, followed by its data type and possibly some additional optional values that we will see later. Each attribute or column definition is separated by a comma. For example, if we want to create a table for provinces in Canada, you would specify create table provinces, open parentheses, ID car, 2, primary key, not null, comma, name varchar, 24, close parentheses. In this example, the data types used are car, which is a character string of a fixed length, in this case 2, and varchar, which is a character string of a variable length. In this case, the variable character field can be up to 24 characters long. Issuing this statement would create a table in the database with two columns. The first column, ID, for storing the abbreviated two-letter province shortcodes, such as AB, BC, etc. And the second column, called name, for storing the full name of the province, such as Alberta, British Columbia, etc. Now let's look at a more elaborate example based on the library database. This database includes several entities such as author, book, borrower, etc. Let's start by creating the table for the author entity. The name of the table will be author, and its attributes such as author_ID, first name, last name, etc. will be the columns of the table. In this table, we will also assign the author_ID attribute as the primary key, so that no duplicate values can exist. Recall, the primary key of a relational table uniquely identifies each tuple or row in a table. To create the author table, issue the following command: create table author, open parentheses, author_ID, car2, primary key not null, comma, last name varchar 15, not null, comma, first name varchar 15, not null, comma, email varchar 40, comma, city varchar 15, comma, country car 2, close parentheses. Note that the author_ID is the primary key. This constraint prevents duplicate values in the table. Also note that the last name and first name have the constraint not null. This ensures that these fields cannot contain a null value, since an author must have a name. Now you know that create is a DDL statement for creating entities or tables in a database. And the create table statement includes definition of attributes of columns in the table, including names of columns, data types of columns, and other optional values if required, such as the primary key constraint. Thanks for watching this video. Hello and welcome to Alter, Drop, and Truncate tables. After watching this video, you will be able to describe the alter table, drop table, and truncate statements, explain the syntax, and use the statements in queries. You use the alter table statement to add or remove columns from a table, to modify the data type of columns, to add or remove keys, and to add or remove constraints. The syntax of the alter table statement is shown here. You start with alter table, followed by the name of the table that you want to alter. Differently to the create table statement, though, you do not use parentheses to enclose the parameters for the alter table statement. Each row in the alter table statement specifies one change that you want to make to the table. For example, to add a telephone number column to the author table in the library database to store the author's telephone number, use the following statement: alter table author, add column, telephone_number, big int, semicolon. In this example, the data type for the column is big int, which can hold a number up to 19 digits long. You can also use the alter table statement to modify the data type of a column. To do this, use the alter column clause specifying the new data type for the column. For example, using a numeric data type for telephone number means that you cannot include parentheses, plus signs, or dashes as part of the number. You can change the column to use the car data type to overcome this. This code shows how to alter the author table. Alter table author, alter column telephone_number, set data type car, open parentheses, 20, close parentheses, semicolon. Altering the data type of a column containing existing data can cause problems, though, if the existing data is not compatible with the new data type. For example, changing a column from the car data type to a numeric data type will not work if the column already contains non-numeric data. If you try to do this, you will see an error message in the notification log and the statement will not run. If your spec changes and you no longer need this extra column, you can again use the alter table statement, this time with the drop column clause to remove the column as shown. Alter table author drop column telephone_number, semicolon. Similar to using drop column to delete a column from a table, you use the drop table statement to delete a table from a database. If you delete a table that contains data, by default the data will be deleted alongside the table. The syntax for the drop table statement is drop table, table underscore name, semicolon. So you use this statement, drop table author, semicolon, to remove the table from the database. Sometimes you might want to just delete the data in a table rather than deleting the table itself. While you can use the delete statement without a where clause to do this, it is generally quicker and more efficient to truncate the table instead. You use the truncate table statement to delete all of the rows in a table. The syntax of this statement is truncate table, table underscore name, immediate, semicolon. The immediate specifies to process the statement immediately and that it cannot be undone. So, to truncate the author table, you use this statement, truncate table, author immediate, semicolon. In this video, you learned that the alter table statement changes the structure of an existing table, for example, to add, modify, or drop columns. The drop table statement deletes an existing table, and the truncate table statement deletes all rows of data in a table.
Hello, and welcome to Retrieving Data with Select Statement String Patterns. In this video, we will learn about some advanced techniques in retrieving data from a relational database table. At the end of this lesson, you will be able to describe how to simplify a select statement by using string patterns, ranges, or sets of values. The main purpose of a database management system is not just to store the data, but also facilitate retrieval of the data. In its simplest form, a select statement is select star from table name. Based on our simplified library database model and the table book, select star from book gives a result set of 4 rows. All the data rows for all columns in the table book are displayed. Or you can retrieve a subset of columns, for example, just 2 columns from the table book, such as book underscore ID and title. Or you can restrict the result set by using the where clause. For example, you can select the title of the book whose book underscore ID is B1. But what if we don't know exactly what value to specify in the where clause? The where clause always requires a predicate, which is a condition that evaluates to true, false, or unknown. But what if we don't know exactly what value the predicate is? For example, what if we can't remember the name of the author, but we remember that their first name starts with R? In a relational database, we can use string patterns to search data rows that match this condition. Let's look at some examples of using string patterns. If we can't remember the name of the author, but we remember that their name starts with R, we use the where clause with the like predicate. The like predicate is used in a where clause to search for a pattern in a column. The percent sign is used to define missing letters. The percent sign can be placed before the pattern, after the pattern, or both before and after the pattern. In this example, we use the percent sign after the pattern, which is the letter R. The percent sign is called a wildcard character. A wildcard character is used to substitute other characters. So, if we can't remember the name of the author, but we can remember that their first name starts with the letter R, we add the like predicate to the where clause. For example, select first name from author, where first name like R percentile. This will return all rows in the author table whose author's first name starts with the letter R. And here is the result set. 2 rows are returned for authors Raoul and Rav. What if we wanted to retrieve the list of books whose number of pages is more than 290 but less than 300? We could write the select statement like this, specifying the where clause as where pages is greater than or equal to 290 and pages is less than or equal to 300. But in a relational database, we can use a range of numbers to specify the same condition. Instead of using the comparison operators greater than or equal to, we use the comparison operator between and. Between and compares 2 values. The values in the range are inclusive. In this case, we rewrite the query to specify the where clause as where pages between 290 and 300. The result set is the same, but the select statement is easier and quicker to write. In some cases, there are data values that cannot be grouped under ranges. For example, if we want to know which countries the authors are from. If we wanted to retrieve authors from Australia or Brazil, we could write the select statement with the where clause repeating the two country values. However, what if we want to retrieve authors from Canada, India, and China? The where clause would become very long, repeatedly listing the required country conditions. Instead, we can use the in operator. The in operator allows us to specify a set of values in a where clause. This operator takes a list of expressions to compare against. In this case, the countries Australia or Brazil. Now you can describe how to simplify a select statement by using string patterns, ranges, or sets of values. Thanks for watching this video. Hello, and welcome to Sorting Select Statement Result Sets. In this video, we will learn about some advanced techniques in retrieving data from a relational database table and sorting how the result set displays. At the end of this lesson, you will be able to describe how to sort the result set by either ascending or descending order and explain how to indicate which column to use for the sorting order. The main purpose of a database management system is not just to store the data, but also facilitate retrieval of the data. In its simplest form, a select statement is select star from table name. Based on our simplified library database model and the table book, select star from book gives a result set of 4 rows. All the data rows for all columns in the table book are displayed. We can choose to list the book titles only, as shown in this example. Select title from book. However, the order does not seem to be in any order. Displaying the result set in alphabetical order would make the result set more convenient. To do this, we use the order by clause. To display the result set in alphabetical order, we add the order by clause to the select statement. The order by clause is used in a query to sort the result set by a specified column. In this example, we have used order by on the column title to sort the result set. By default, the result set is sorted in ascending order. In this example, the result set is sorted in alphabetical order by book title. To sort in descending order, use the keyword des. The result set is now sorted according to the column specified, which is title, and is sorted in descending order. Notice the order of the first 3 rows. The first 3 words of the title are the same, so the sorting starts from the point where the characters differ. Another way of specifying the sort column is to indicate the column sequence number. In this example, select title, pages from book, order by 2 indicates the column sequence number in the query for the sorting order. Instead of specifying the column name pages, the number 2 is used. In the select statement, the second column specified in the column list is pages, so the sort order is based on the values in the pages column. In this case, the pages column indicates the number of pages in the book. As you can see, the result set is in ascending order by number of pages. Now you can describe how to sort the result set by either ascending or descending order, and explain how to indicate which column to use for the sorting order. Thanks for watching this video. Hello, and welcome to Grouping Select Statement Result Sets. In this video, we will learn about some advanced techniques in retrieving data from a relational database table, and sorting and grouping how the result set displays. At the end of this lesson, you will be able to explain how to eliminate duplicates from a result set, and describe how to further restrict a result set. At times, a select statement result set can contain duplicate values. Based on our simplified library database model, in the author table example, the country column lists the 2-letter country code of the author's country. If we select just the country column, we get a list of all of the countries. For example, select country from author order by 1. The order by clause sorts the result set. This result set lists the countries the authors belong to, sorted alphabetically by country. In this case, the result set displays 20 rows, 1 row for each of the 20 authors. But some of the authors come from the same country, so the result set contains duplicates. However, all we need is a list of countries the authors come from. So in this case, duplicates do not make sense. To eliminate duplicates, we use the keyword distinct. Using the keyword distinct reduces the result set to just 6 rows. But what if we wanted to also know how many authors come from the same country? So now we know that the 20 authors come from 6 different countries. But we might want to also know how many authors come from the same country. To display the result set listing the country and number of authors that come from that country, we add the group by clause to the select statement. The group by clause groups a result into subsets that has matching values for one or more columns. In this example, countries are grouped and then counted using the count function. Notice the column heading for the second column in the result set. The numeric value 2 displays as a column name because the column name is not directly available in the table. The second column in the result set was calculated by the count function. Instead of using the column name 2, we can assign a column name to the result set. We do this using the as keyword. In this example, we change the derived column name 2 to column name count using the as count keyword. This helps clarify the meaning of the result set. Now that we have the count of authors from different countries, we can further restrict the number of rows by passing some conditions. For example, we can check if there are more than 4 authors from the same country. To set a condition to a group by clause, we use the keyword having. The having clause is used in combination with the group by clause. It is very important to note that the where clause is for the entire result set, but the having clause works only with the group by clause. To check if there are more than 4 authors from the same country, we add the following to the select statement. Having count country greater than 4. Only countries that have 5 or more authors from that country are listed in the result set. In this example, those countries are China with 6 authors and India also with 6 authors. Now you can explain how to eliminate duplicates from a result set and describe how to further restrict a result set. Thanks for watching this video.
Hello and welcome. In this video, we'll go over SQL functions built into the database. So let's get started. While it is very much possible to first fetch data from a database and then perform operations on it from your applications and notebooks, most databases come with built-in functions. These functions can be included in SQL statements, allowing you to perform operations on data right within the database itself. Using database functions can significantly reduce the amount of data that needs to be retrieved from the database, that is, reduces network traffic and use of bandwidth. When working with large data sets, it may be faster to use built-in functions rather than first retrieving the data into your application and then executing functions on the retrieved data. Note that it is also possible to create your own functions, that is, user-defined functions, in the database, but that is a more advanced topic. For the examples in this lesson, let's consider this pet rescue table in the database for a pet rescue organization. It records rescue transaction details and includes the columns ID, animal, quantity, cost, and rescue date. For the purposes of this lesson, we have populated it with several rows of data as shown here. What are aggregate or column functions? An aggregate function takes a collection of like values, such as all of the values in a column, as input and returns a single value, or null. Examples of aggregate functions include sum, minimum, maximum, average, etc. Let's look at some examples based on the pet rescue table. The sum function is used to add up all the values in a column. To use the function, you write the column name within parentheses after the function name. For example, to add up all of the values in the cost column, select sum cost from pet rescue. When you use an aggregate function, the column in the result set by default is given a number. It is possible to explicitly name the resulting column. For example, let's say we want to call the output column in the previous query as sum of cost. Select sum cost as sum of cost from pet rescue. Note the use of as in this example. Minimum, as the name implies, is used to get the lowest value. Similarly, maximum is used to get the highest value. For example, to get the maximum quantity of any animal rescue in a single transaction, select Max Quantity from Pet Rescue. Aggregate functions can also be applied on a subset of data instead of an entire column. For example, to get the minimum quantity of ID column for dogs, select min ID from Pet Rescue where animal equals dog. The average function is used to return the average or the mean value. For example, to specify the average value of cost as select average cost from Pet Rescue. Note that we can perform mathematical operations between columns and then apply aggregate functions on them. For example, to calculate the average cost per dog, select average cost divided by quantity from Pet Rescue where animal equals dog. In this case, the cost is for multiple units, so we first divide the cost by the quantity of the rescue. Now let's look at the scalar and string functions. Scalar functions perform operations on individual values. For example, to round up or down every value in the cost column to the nearest integer, select Round Cost from Pet Rescue. There is a class of scalar functions called string functions that can be used for operations on strings, that is, char and varchar values. For example, to retrieve the length of each value in animal column, select Length Animal from Pet Rescue. Uppercase and lowercase functions can be used to return uppercase or lowercase values of strings. For example, to retrieve animal values in uppercase, select Uppercase Animal from Pet Rescue. Scalar functions can be used in the where clause. For example, to get lowercase values of the animal column for cat, select star from Pet Rescue where lowercase animal equals cat. This type of a statement is useful for matching values in the where clause if you are not sure whether the values are stored in upper, lower, or mixed case in the table. You can also have one function operate on the output of another function. For example, to get unique cases for animal column in uppercase, select Distinct Uppercase Animal from Pet Rescue. In this video, we looked at some built-in SQL aggregate functions, such as sum, minimum, maximum, and average. We also looked at scalar and string functions, such as round, lowercase, and uppercase. Thank you for watching. Hello and welcome. In this video, we'll go over date and time SQL functions built into the database. So let's get started. Most databases contain special data types for dates and times. DB2 contains date, time, and timestamp types. In DB2, date has 8 digits for year, month, and day. Time has 6 digits, hours, minutes, and seconds. Timestamp has 20 digits, year, month, day, hour, minute, seconds, and microseconds, where double X represents month and 6 Z's or Z's represents microseconds. Functions exist to extract the day of week, day of year, week, hour, minute, and second. Let us look at some examples of queries for date and time functions. The day function can be used to extract the day portion from a date. For example, to get the day portion for each rescue date involving cat, select day, rescue date, from Pet Rescue, where animal equals cat. Date and time functions can be used in the where clause. For example, to get the number of rescues during the month of May, that is, for month 5, select Count star from Pet Rescue, where month rescue date equals 05. You can also perform date or time arithmetic. For example, to find out what date it is 3 days after each rescue date. Maybe you want to know this because the rescue needs to be processed within 3 days. Select Rescue Date plus 3 days from Pet Rescue. Special registers current time and current date are also available. For example, to find out how many days have passed since each rescue date till now, select Current Date minus Rescue Date from Pet Rescue. The result will be in years, months, days. In this video, we looked at different types of built-in SQL functions for working with dates and times. Thank you for watching.
Hello and welcome. In this video, you'll learn how to write subqueries or nested select statements. Subqueries or subselects are like regular queries but placed within parentheses and nested inside another query. This allows you to form more powerful queries than would have been otherwise possible. An example of a nested query is shown. In this example, the subquery is inside the where clause of another query. Consider the employees table from the previous video. The first few rows of data are shown here. The table contains several columns, including an employee ID, first name, last name, salary, etc. We will now go over some examples involving this table. Let's consider a scenario which may necessitate the use of subqueries. Let's say we want to retrieve the list of employees who earn more than the average salary. To do so, we could try this code. Select star from employees where salary is greater than average salary. However, running this query will result in an error like the one shown, indicating an invalid use of the aggregate function. One of the limitations of built-in aggregate functions, like the average function, is that they cannot always be evaluated in the where clause. So, to evaluate a function like average in the where clause, we can make use of a subselect expression like the one shown here. Select employee ID, first name, last name, salary from employees where salary is less than, open parenthesis, select average salary from employees, close parenthesis. Notice that the average function is evaluated in the first part of the subquery, allowing us to circumvent the limitation of evaluating it directly in the where clause. The subselect doesn't just have to go in the where clause. It can also go in other parts of the query, such as in the list of columns to be selected. Such subqueries are called column expressions. Now, let's look at a scenario where we might want to use a column expression. Say we wanted to compare the salary of each employee with the average salary. We could try a query like select employee ID, salary, average salary as average salary from employees. Running this query will result in an error indicating that no group by clause is specified. We can circumvent this error by using the average function in a subquery placed in the list of the columns. For example, select employee ID, salary, open left parenthesis, select average salary from employees, closed right parenthesis, as average salary from employees. Another option is to make the subquery be part of the from clause. Subqueries like these are sometimes called derived tables or table expressions because the outer query uses the results of the subquery as a data source. Let's look at an example to create a table expression that contains non-sensitive employee information. select star from Select Employee ID, first name, last name, department ID from employees as employee for all. The derived table in the subquery does not include sensitive fields like date of birth or salary. This example is a trivial one, and we could just as easily have included the columns in the outer query. However, such derived tables can prove to be powerful in more complex situations, such as when working with multiple tables and doing joins. In this video, you have seen how subqueries and nested queries can be used to form richer queries, and how they can overcome some of the limitations of aggregate functions. You also learned to use subqueries in the where clause, in the list of columns, and in the from clause. Thanks for watching this video.
Hello and welcome.
In this video, you will learn how to write queries that access more than one table. There are several ways to access multiple tables in the same query, namely using subqueries, implicit join, and join operators, such as inner join and outer join. In this video, we'll examine the first two options. The third option is covered in more detail in other videos. Let's consider the employees and departments tables from a previous video. The employees table contains several columns for categories such as employee ID, first name, last name, and salary, to name a few. The departments table contains a department ID, department name, manager ID, and location ID. Some sample data from these tables is shown here. We will utilize these tables for the examples in this video. In a previous video, we learned how to use subqueries. Now, let's use subqueries to work with multiple tables. If we want to retrieve only the employee records from the employees table for which a department ID exists in the departments table, we can use a subquery as follows. Select star from employees, where department ID in, select department ID, department from departments. Here the outer query accesses the employees table, and the subquery on the departments table is used for filtering the result set of the outer query. Let's say we want to retrieve only the list of employees from a specific location. We do not have any location information in the employees table, but the departments table has a column called location ID. Therefore, we can use a subquery from the departments table as input to the employee table query as follows. Select star from employees, where department ID in, select department ID, department from departments, where location ID equals L0002. Now, let's retrieve the department ID and department name for employees who earn more than $70,000. To do so, we will need a subquery on the employees table to satisfy the salary criteria, and then feed it as input to an outer query on the departments table in order to get the matching department info. Select department ID, department, department name from departments, where department ID, department in, select department ID from employees where salary is greater than $70,000. We can also access multiple tables by specifying them in the from clause of the query. Consider the example, select star from employees, departments. Here we specified two tables in the from clause. This results in a table join, but note we are not explicitly using the join operator. The resulting join in this example is called a full join, or Cartesian join, because every row in the first table is joined with every row in the second table. If you examine the result set, you will see more rows than in both tables individually. We can use additional operands to limit the result set. Let's look at an example where we limit the result set to only rows with matching department IDs. Select star from Employees, Departments, where Employees Department ID equals Departments, Department ID, Department. Notice that in the Where clause, we prefix the name of the column with the name of the table. This is to fully qualify the column name, since it's possible that different tables could have some column names that are exactly the same. Since the table names can sometimes be long, we can use shorter aliases for table names as shown here. Select star from Employees E, Departments D, where E, Department ID, equals D, Department ID, Department. Here we define the alias E for Employees table and D for Departments table, and then use these aliases in the Where clause. If we wanted to see the department name for each employee, we would enter the code as follows. Select Employee ID, Department Name from Employees E, Departments D, where E, Department ID equals D, Department ID, Department. Similar to before, the column names in the Select clause can also be prefixed by aliases, as shown in the query. Select E Employee ID, D Department ID, Department, from Employees E Departments D, where E Department ID equals D Department ID, Department. In this lesson, we have shown you how to work with multiple tables using subqueries and implicit joins. Thanks for watching.
Hello! In this video, you will learn how to access databases using Python. Databases are powerful tools for data scientists. After completing this module, you will be able to explain the basic concepts related to using Python to connect to databases. Then you will create tables, load data, and query data using SQL from Jupyter Notebooks, and finally, analyze the data. In the lab assignments, you will learn how to create an instance in the cloud, connect to a database, query data from the database using SQL, and analyze the data using Python. You will be able to explain the basic concepts related to connecting a Python application to a database, describe SQL APIs, as well as list some of the proprietary APIs used by popular SQL-based DBMS systems. Let's quickly review some of the benefits of using Python, a popular scripting language for connecting to databases. The Python ecosystem is very rich and provides easy-to-use tools for data science. Some of the most popular packages are NumPy, Pandas, Matplotlib, and SciPy. Python is easy to learn and has a simple syntax. Due to its open-source nature, Python has been ported to many platforms. All your Python programs can work on any of these platforms without requiring any changes at all, if you are careful and avoid any system-dependent features. Python supports relational database systems. Writing Python code to access databases is made easier by the presence of the Python Database API, commonly referred to as the DB API. And detailed documentation related to Python is easily available. Notebooks are also very popular in the field of data science because they run in an environment that allows creation and sharing of documents that contain live code, equations, visualizations, and explanatory text. A notebook interface is a virtual notebook environment used for programming. Examples of notebook interfaces include the Mathematica Notebook, Maple Worksheet, MATLAB Notebook, IPython Jupyter, R Markdown, Apache Zeppelin, Apache Spark Notebook, and the Databricks Cloud. In this module, we will be using Jupyter Notebooks. The Jupyter Notebook is an open-source web application that allows you to create and share documents that contain live code, equations, visualizations, and narrative text. Here are some of the advantages of using Jupyter Notebooks. Notebooks support for over 40 programming languages, including Python, R, Julia, and Scala. Notebooks can be shared with others by email, Dropbox, GitHub, and the Jupyter Notebook Viewer. Your code can produce rich interactive output, HTML, images, videos, LaTeX, and custom MIME types. You can leverage big data tools such as Apache Spark from Python, R, and Scala, and explore that same data with Pandas, scikit-learn, ggplot2, and TensorFlow. This is how a typical user accesses databases using Python code written on a Jupyter Notebook, a web-based editor. There is a mechanism by which the Python program communicates with the DBMS. The Python code connects to the database using API calls. We will explain the basics of SQL APIs and Python DB APIs. An application programming interface is a set of functions that you can call to get access to some type of service. A SQL API consists of library function calls as an application programming interface API for the DBMS. To pass SQL statements to the DBMS, an application program calls functions in the API, and it calls other functions to retrieve query results and status information from the DBMS. The basic operation of a typical SQL API is illustrated in the figure. The application program begins its database access with one or more API calls that connect the program to the DBMS. To send a SQL statement to the DBMS, the program builds the statement as a text string in a buffer and then makes an API call to pass the buffer contents to the DBMS. The application program makes API calls to check the status of its DBMS request and to handle errors. The application program ends its database access with an API call that disconnects it from the database. Now let's learn basic concepts about some of the proprietary APIs used by popular SQL-based DBMS systems. Each database system has its own library. As you can see, the table shows a list of a few applications and corresponding SQL APIs. MySQL-C API provides low-level access to the MySQL client server protocol and enables C programs to access database contents. The PsychoPG2 API connects Python applications in PostgreSQL databases. The IBM_DB API is used to connect Python applications to IBM DB2 databases. The DBlib API is used to connect to SQL Server databases. ODBC is used for database access for Microsoft Windows OS. OCI is used by Oracle databases. And finally, JDBC is used by Java applications. Thanks for watching this video.
Hello and welcome to Writing Code using DB API. After completing this video, you will be able to explain the basic concepts related to the Python DB API and database cursors, and also write code using DB APIs. As we saw in the beginning of this module, the user writes Python programs using a Jupyter Notebook. There is a mechanism by which the Python code communicates with the DBMS. The Python code connects to the database using DB API calls. DB API is Python's standard API for accessing relational databases. It is a standard that allows you to write a single program that works with multiple kinds of relational databases, instead of writing a separate program for each one. So, if you learn the DB API functions, then you can apply that knowledge to use any database with Python. Here are some advantages of using the DB API. It's easy to implement and understand. This API has been defined to encourage similarity between the Python modules that are used to access databases. It achieves consistency, which leads to more easily understood modules. The code is generally more portable across databases, and it has a broader reach of database connectivity from Python. As we know, each database system has its own library. As you can see, the table shows a list of a few databases and corresponding DB APIs to connect to Python applications. The IBM_DB library is used to connect to an IBM DB2 database. The MySQL connector Python library is used to connect to a Compose for MySQL database. The PsychoPG2 library is used to connect to a Compose from PostgreSQL database. And finally, the PyMongo library is used to connect to a Compose from MongoDB database. The two main concepts in the Python DB API are connection objects and query objects. You use connection objects to connect to a database and manage your transactions. Cursor objects are used to run queries. You open a cursor object and then run queries. The cursor works similar to a cursor in a text processing system, where you scroll down in your results set and get your data into the application. Cursors are used to scan through the results of a database. The DB API includes a connect constructor for creating a connection to the database. It returns a connection object, which is then used by the various connection methods. These connection methods are the cursor method, which returns a new cursor object using the connection, the commit method, which is used to commit any pending transaction to the database, the rollback method, which causes the database to roll back to the start of any pending transaction, the close method, which is used to close a database connection. These objects represent a database cursor, which is used to manage the content of a fetch operation. Cursors created from the same connection are not isolated. That is, any changes done to the database by a cursor are immediately visible by the other cursors. Cursors created from different connections can or cannot be isolated depending on how the transaction support is implemented. A database cursor is a control structure that enables transversal over the records in a database. It behaves like a file name or file handle in a programming language. Just as a program opens a file to access its contents, it opens a cursor to gain access to the query results. Similarly, the program closes a file to end its access and closes a cursor to end access to the query results. Another similarity is that just as file handle keeps track of the program's current position within an open file, a cursor keeps track of the program's current position within the query results. Let's walk through a Python application that uses the DB API to query a database. First, you import your database module by using the Connect API from that module. To open a connection to the database, you use the Connect constructor and pass in the parameters, that is, the database name, username, and password. The Connect function returns connection object. After this, you create a cursor object on the connection object. The cursor is used to run queries and fetch results. After running the queries using the cursor, we also use the cursor to fetch the results of the query. Finally, when the system is done running the queries, it frees all resources by closing the connection. Remember that it is always important to close connections to avoid unused connections taking up resources. Thanks for watching this video.
Hello, and welcome to connecting to a database using the IBM_DB API. After completing this lesson, you will be able to understand the IBM_DB API, as well as the credentials required to connect to a database using Python. We will also demonstrate how to connect to an IBM DB2 database using Python code written on a Jupyter notebook. The IBM_DB API provides a variety of useful Python functions for accessing and manipulating data in an IBM data server database, including functions for connecting to a database, preparing and issuing SQL statements, fetching rows from result sets, calling stored procedures, committing and rolling back transactions, handling errors, and retrieving metadata. The IBM_DB API uses the IBM Data Server driver for ODBC and CLI APIs to connect to IBM DB2 and Informix. We import the IBM_DB library into our Python application. Connecting to the DB2 requires the following information: a driver name, a database name, a host DNS name or IP address, a host port, a connection protocol, a user ID, and a user password. Here is an example of creating a DB2 database connection in Python. We create a connection object, DSN, which stores the connection credentials. The connect function of the IBM_DB API will be used to create a non-persistent connection. The DSN object is passed as a parameter to the connection function. If a connection has been established with the database, then the code returns connected as the output, otherwise the output will be unable to connect to database. Then we free all resources by closing the connection. Remember that it is always important to close connections so that we can avoid unused connections taking up resources. Thank you for watching this video. Hello and welcome to creating tables, loading data, and querying data. After completing this lesson, you will be able to understand basic concepts related to creating tables, loading data, and querying data using Python, as well as demonstrate an example of how to perform these tasks using the IBM DB2 on Cloud database and Jupyter notebooks. For this example, we will be using DB2 as the database. We first obtain a connection resource by connecting to the database by using the connect method of the IBM_DB API. There are different ways of creating tables in DB2. One is using the web console provided by DB2, and the other option is to create tables from any SQL, R, or Python environments. Let's take a look at how to create tables in DB2 from our Python application. Here is a sample table of a commercial trucks database. Let's see how we can create the trucks table in the DB2 using Python code. To create a table, we use the IBM_DB exec_immediate function. The parameters for the function are connection, which is a valid database connection resource that is returned from the IBM_DB connect or IBM_DB pconnect function. Statement, which is a string that contains the SQL statement. And options, which is an optional parameter that includes a dictionary that specifies the type of cursor to return for result sets. Here is the code to create a table called trucks in Python. We use the IBM_DB exec_immediate function of the IBM_DB API. The connection resource that was created is passed as the first parameter to this function. The next parameter is the SQL statement, which is the create table query used to create the trucks table. The new table created will have 5 columns. Serial_no will be the primary key. Now let's take a look at loading data. We use the IBM_DB exec_immediate function of the IBM_DB API. The connection resource that was created is passed as the first parameter to this function. The next parameter is the SQL statement, which is the insert into query used to insert data in the trucks table. A new row will be added to the trucks table. Similarly, we add more rows to the trucks table using the IBM_DB exec_immediate function. Now that your Python code has been connected to a database instance and the database table has been created and populated with data, let's see how we can fetch data from the trucks table that we created on DB2 using Python code. We use the IBM_DB exec_immediate function of the IBM_DB API. The connection resource that was created is passed as the first parameter to this function. The next parameter is the SQL statement, which is the select from table query. The Python code returns the output, which shows the fields of the data in the trucks table. You can check if the output returned by the select query shown is correct by referring to the DB2 console. Let's look at how we can use pandas to retrieve data from the database tables. Pandas is a popular Python library that contains high-level data structures and manipulation tools designed to make data analysis fast and easy in Python. We load data from the trucks table into a data frame called df. A data frame represents a tabular spreadsheet-like data structure containing an ordered collection of columns, each of which can be a different value type. Thanks for watching this video. Hello, and welcome to Analyzing Data with Python. After completing this video, you will be able to understand basic concepts related to performing exploratory analysis on data. We will demonstrate an example of how to store data using the IBM DB2 on Cloud database, and then use Python to do some basic data analysis on this data. In this video, we will be using the McDonald's menu nutritional facts data for popular menu items at McDonald's, while using Python to perform basic exploratory analysis. McDonald's is an American fast food company and the world's largest restaurant chain by revenue. Although McDonald's is known for fast food items such as hamburgers, French fries, soft drinks, milkshakes, and desserts, the company has added to its menu salads, fish, smoothies, and fruit. McDonald's provides nutrition analysis of their menu items to help you balance your McDonald's meal with other foods you eat. The dataset used in this lesson has been obtained from the Nutritional Facts for McDonald's menu from Kaggle. We need to create a table on DB2 to store the McDonald's menu nutrition facts dataset that we will be using. We will also be using the console provided by DB2 for this process. There are 4 steps involved in loading data into a table: source, target, define, and finalize. We first load the spreadsheet into the DB2 using the console. We then select the target schema, and then you will be given an option to load the data into an existing table or create a new table. When you choose to create a new table, you have the option to specify the table name. Next, you will see a preview of the data where you can also define the columns and data types. Review the settings and begin the load. When the loading is complete, you can see the statistics on the loaded data. Next, view the table to explore further. DB2 allows you to analyze data using in-database analytics, APIs, RStudio, or Python. The data has been loaded into our relational database. You can run Python scripts that retrieve data from and write data to a DB2 database. Such scripts can be powerful tools to help you analyze your data. For example, you can use them to generate statistical models based on data in your database, and to plot the results of these models. In this lesson, we will be using Python scripts that will be run within a Jupyter notebook. Now, after obtaining a connection resource by connecting to the database by using the connect method of the IBM_DB API, we use the SQL select query to verify the number of rows that have been loaded in the table created. The figure shows a snapshot of the output. The output obtained is 260, which is similar to the number of rows in the DB2 console. Now let's see how we can use pandas to retrieve data from the database tables. We load data from the McDonald's_nutrition table into the data frame df using the read_SQL method. The SQL select query and the connection object are passed as parameters to the read_SQL method. We can view the first few rows of the data frame df that we created using the head method. Now it's time to learn about your data. Pandas methods are equipped with a set of common mathematical and statistical methods. Let's use the describe method to view the summary statistics of the data in the data frame. Then explore the output of the describe method. We see that there are 260 observations or food items in our data frame. We also see that there are 9 unique categories of food items in our data frame. We can also see summary statistics information such as frequency, mean, median, standard deviation, etc. for the 260 food items across the different variables. For example, the maximum value for total fat is 118. Let's investigate this data further. Let's try to understand one of the nutrients in the food items, which is sodium. A main source of sodium is table salt. The average American eats 5 or more teaspoons of salt each day. This is about 20 times as much as the body needs. Sodium is found naturally in foods, but a lot of it is added during processing and preparation. Many foods that do not taste salty may still be high in sodium. Large amounts of sodium can be hidden in canned, processed, and convenience foods. Sodium controls fluid balance in our bodies and maintains blood volume and blood pressure. Eating too much sodium may raise blood pressure and cause fluid retention, which could lead to swelling of the legs and feet or other health issues. When limiting sodium in your diet, a common target is to eat less than 2,000 milligrams of sodium per day. Now, using the nutrition data set from McDonald's, let's do some basic data analysis to answer the question: which food item has the maximum sodium content? We first use visualization to explore the sodium content of food items. Using the swarm plot method provided by the Seaborn package, we create a categorical scatter plot as shown on the right. Then give, as the input, category on the x-axis, sodium on the y-axis, and the data will be the data frame DF that contains the nutritional data set from McDonald's. The plot shows the sodium values for the different food items by category. Notice a high value of around 3,600 for sodium on the scatter plot. We will be learning about visualizations later in this module. Let's further explore this high sodium value and identify which food items on the menu have this value for sodium. Let's do some basic data analysis using Python to find which food items on the menu have maximum sodium content. To check the values of sodium levels in the food items within the dataset, we use the code as shown in Code 1. The describe method is used to understand the summary statistics associated with sodium. Notice that the maximum value of sodium is given as 3,600. Now let's further explore the row associated with the maximum sodium variable as shown in Code 2. We use the IDX max method to compute the index values at which the maximum value of sodium is obtained in the data frame. We see that the output is 82. Now let's find the item name associated with the 82nd item in our data frame. As shown in Code 3, we will use the .at method to find the item name by passing the index of 82 and the column name item to be returned for the 82nd row. Finally, we find that the food item on the menu that has the highest sodium content is Chicken McNuggets, 40 pieces. Visualizations are very useful for initial data exploration. They can help us understand relationships, patterns, and outliers in the data. Let's first create a scatter plot with protein on the x-axis and total fat on the y-axis. Scatter plots are very popular visualization tools and show the relationship between two variables with a point for each observation. To do this, we can use the joint plot function provided by the Seaborn package and give as input protein on the x-axis and total fat on the y-axis. And the data will be the data frame DF that contains the nutritional data set from McDonald's. The output scatter plot is shown on the right side. The plot has an interesting shape. It shows the correlation between the two variables, protein and fat. Correlation is a measure of association between two variables and has a value of between -1 and +1. We see that the points on the scatter plot are closer to a straight line in the positive direction, so we have a positive correlation between the two variables. On the top right corner of the scatter plot, we have the values of the Pearson correlation, 0.81, and the significance of the correlation denoted as p, which is a good value that shows the variables are certainly correlated. The plot also shows two histograms, one on the top and the other on the right side. The histogram on the top is that of the variable protein, and the histogram on the right side is that of the variable total fat. We also notice that there is a point on the scatter plot outside the general pattern. This is a possible outlier. Now let's see how we can visualize data using box plots. Box plots are charts that indicate the distribution of one or more variables. The box in a box plot captures the middle 50% of data. Lines and points indicate possible skewness and outliers. Let's create a box plot for sugar. The function we are going to use is boxplot from the Seaborn package. We give the column name sugars as input to the boxplot function. The output is shown on the right side, where we have the boxplot with average values of sugar in food items around 30 grams. We also notice a few outliers that indicate food items with extreme values of sugar. There exists food items in the dataset that have sugar content of around 128 grams. Candies may be among these high sugar content food items on the menu. Now that you know how to do basic exploratory data analysis using pandas and visualization tools, proceed to the labs in this module where you can practice the concepts learned. Thank you for watching this video.
Hello and welcome. In this video, we'll give you a few hints and tips for working with real-world datasets. Many of the real-world datasets are made available as .csv files. These are text files which contain data values typically separated by commas. In some cases, a different separator, such as a semicolon, may be used. For this video, we will use an example of a file called dogs.csv. Although this is a fictional dataset that contains names of dogs and their breeds, we will use it to illustrate concepts that you will then apply to real datasets. Sample contents of the dogs.csv file are shown here. The first row in the table, in many cases, contains attribute labels, which map to column names in a table. In dogs.csv, the first row contains the name of 3 attributes. ID is the name of the first attribute, and the subsequent rows contain ID values of 1, 2, and 3. The name of the dog is the second attribute. In this case, the dog names, Wolfie, Fluffy, and Huggy, are the values. And the third attribute is called breed, either the dominant breed or pure breed name. It has values of German Shepherd, Pomeranian, and Labrador. As we've just seen, CSV files can have the first or a header row that contains the names of the attributes. If you're loading the data into the database using the Visual Load tool in the database console, ensure the header in first row is enabled. This will map the attribute names in the first row of the CSV file into column names in the database table, and the rest of the rows into the data rows in the table, as shown here. Note that the default column names may not always be database or query friendly, and if that is the case, you may want to edit them before the table is created. Now, let's talk about querying column names that are lower or mixed case, that is, a combination of upper and lower case. Let's assume we loaded the dogs.csv file using the default column names from the CSV. If we try to retrieve the contents of the ID column using the query select lowercase ID from dogs, we'll get an error, as shown, indicating the ID is not valid. This is because the database parser assumes uppercase names by default, whereas when we loaded the CSV file into the database, it had the ID column name in mixed case, i.e., an uppercase I and a lowercase d. In this case, to select data from a column with a mixed case name, we need to specify the column name in its correct case within double quotes, as follows. Select double quotes, uppercase I, lowercase d, end double quotes from dogs. Ensure you use double quotes around the column name and not single quotes. Next, we'll cover querying column names that have spaces and other characters. In a CSV file, if the name of the column contains spaces, by default the database may map them to underscores. For example, in the name of dog column, there are spaces in between the 3 words. The database may change it to name underscore of underscore dog. Other special characters like parentheses or brackets may also get mapped to underscores. Therefore, when you write a query, ensure you use proper case formatting within quotes and substitute special characters to underscores, as shown in this example. Select ID, name of dog, breed, dominant breed if not pure breed, from dogs. Please note the underscores separating the words within double quotes. Also, note the double underscore between breed and dominant as shown. Finally, it's also important to note the trailing underscore after the word breed near the end of the query. This is used in place of the closing bracket. When using quotes in Jupyter Notebooks, you may be issuing queries in a notebook by first assigning them to Python variables. In such cases, if your query contains double quotes, for example, to specify a mixed case column name, you could differentiate the quotes by using single quotes for the Python variable to enclose the SQL query and double quotes for the column names. For example, select query equals open single quote select ID in double quotes from dogs close single quote. Now, what if you need to specify single quotes within the query, for example, to specify a value in the where clause? In this case, you can use / as the escape character as follows. Select query equals open single quote select star from dogs where open double quote name of dog close double quote equals / single quote Huggy / single quote close single quote. If you have very long queries, such as join queries or nested queries, it may be useful to split the query into multiple lines for improved readability. In Python notebooks, you can use the / character to indicate continuation to the next row, as shown in this example. %SQL select ID, name of dog, / from dogs, / where name of dog equals Huggy. It would be helpful at this point to take a moment to review the special characters as shown. Please keep in mind that you might get an error if you split the query into multiple lines in a Python notebook without the \. When using SQL Magic, you can use the double %SQL in the first line of the cell in Jupyter Notebooks. It implies that the rest of the content of the cell is to be interpreted by SQL Magic. For example, double %SQL, new row, select ID, name of dog, new row from dogs, new row where name of dog equals Huggy. Again, please note the special characters as shown. When using double %SQL, the / is not needed at the end of each line. At this point, you might be asking, how would you restrict the number of rows retrieved? It's a good question because a table may contain thousands or even millions of rows, and you may only want to see some sample data, or look at just a few rows to see what kind of data the table contains. You may be tempted to just do select star from table name to retrieve the results in a pandas data frame and do a head function on it. But doing so may take a long time for a query to run. Instead, you can restrict the result set by using the limit clause. For example, use the following query to retrieve just the first 3 rows in a table called census data. Select star from census_data limit 3. In this video, we looked at some considerations and tips for working with real-world datasets. Thanks for watching. Hello and welcome. In this video, we'll look at how to get information about tables and their columns in a database. Now, how would you get a list of tables in the database? Sometimes your database may contain several tables and you may not remember the correct name. For example, you may wonder whether the table is called dog, dogs, or four-legged mammals. Database systems typically contain system or catalog tables from where you can query the list of tables and get their properties. In DB2, this catalog is called syscat tables. In SQL Server, it's information schema tables, and in Oracle, it's all tables or user tables. To get a list of tables in a DB2 database, you can run the following query. Select star from syscat tables. This select statement will return too many tables, including system tables, so it's better to filter the result as shown here. Select tab schema, tab name, create underscore time from syscat tables, where tab schema equals ABC12345. Please ensure that you replace ABC12345 with your own DB2 username. When you do a select star from syscat tables, you get all the properties of the tables. Sometimes we're interested in specific properties such as creation time. Let's say you've created several tables with similar names. For example, dog1, dog_test, dogtest1, and so on. But you want to check which of these tables was the last one you created. To do so, you can issue a query like select tab schema, tab name, create underscore time from syscat tables, where tab schema equals QCM 54853. The output will contain the schema name, table name, and creation time for all tables in your schema. Next, let's talk about how to get a list of columns in a table. If you can't recall the exact name of a column, for example, whether it had any lowercase characters or an underscore in its name, in DB2 you can issue a query like the one shown here. Select star from syscat columns where tab name equals dogs. For your information, in MySQL you can simply run the command show columns from dogs. Or you may want to know specific properties like the data type and length of the data type. In DB2, you can issue a statement like select distinct name, call type, length from sys IBM syscolumns where TB name equals dogs. Here we look at the results of retrieving column properties for a real table called Chicago crime data from a Jupyter notebook. Notice in the output you can tell certain column names show different cases. For example, the column titled Arrest has an uppercase A and the rest of the characters are lowercase. So, keep in mind that when you refer to this column in your query, not only must you enclose the word arrest within double quotes, you must also preserve the correct case inside the quotes. In this video, we saw how to retrieve table and column information. Thanks for watching.
Welcome to Views. After watching this video, you will be able to define a view, describe when to use a view, and explain the syntax for creating a view. A view is an alternative way of representing data that exists in one or more tables or views. A view can include all or some of the columns from one or more base tables or existing views. Creating a view creates a named specification of a results table, which can be queried in the same way as a table. You can also change the data in the base table by running insert, update, and delete queries against the view. When you define a view, the definition of the view is stored. The data that the view represents is stored in the base tables, not by the view itself. You can use view to show a selection of data for a given table, so you can omit sensitive data like tax information, birth dates, or salaries. Combine two or more tables in meaningful ways. Simplify access to data by granting access to a view without granting access to the underlying tables, and show only the portions of data relevant to the process that uses the view. For example, you can create a view that displays only non-sensitive data from the employee's table: employee ID, name, address, job ID, manager ID, and department ID. The view does not show sensitive data like salary or birth date. You can use the create view statement to create a view based on one or more tables or views. To define a view, use the create view statement and assign a name, up to 128 characters in length, to the view. List the columns that you want to include. You can use an alias to name the columns if you wish. Use the as select clause to specify the columns in the view, and the from clause to specify the base table name. You can also add an optional where clause to refine the rows in the view. This create view statement creates a view called emph_info based on the employees table. The select statement returns the data in the view as shown in the table below. Views are dynamic. They consist of the data that would be returned from the select statement used to create them. When you use a view in another SQL statement, it behaves as though you have used a select statement that returns the content of the view. The select statement that you use to create the view can name other views and tables, and it can use the where, group by, and having clauses. It cannot use the order by clause or name a host variable. In this example, the emph_info view is created with only the rows where the manager ID is 30002. You can use a select statement to show the information from the view, and verify that only rows where the manager ID is 30002 are included. If you need to remove a view completely, you can use drop view. In this video, you learned that views are an alternative way of accessing data in tables. They can include specified columns from multiple base tables and existing views. Once created, views can be queried like a table, and the data in the base table can be modified through the view. Views are dynamic. Only the definition of the view is stored, not the data, and you can use the create view statement to create a view based on one or more tables or existing views. Welcome to Stored Procedures. After watching this video, you will be able to explain what a stored procedure is, list the benefits of using stored procedures, and describe how to create and use a stored procedure. A stored procedure is a set of SQL or SQL statements that are stored and executed on the database server. So instead of sending multiple SQL statements from the client to the server, you encapsulate them in a stored procedure on the server and send one statement from the client to execute them. You can write stored procedures in many different languages. For example, for DB2 on Cloud and DB2, you can write in SQL PL, PL SQL, Java, C, or other languages. They can accept information as parameters, perform create, read, update, and delete CRUD operations, and return results to the client application. The benefits of stored procedures include reduction in network traffic because only one call is needed to execute multiple statements. Improvement in performance because the processing happens on the server where the data is stored, with just the final result being passed back to the client. Reuse of code because multiple applications can use the same stored procedure for the same job. And an increase in security because A, you do not need to expose all of your table and column information to client-side developers, and B, you can use server-side logic to validate data before accepting it into the system. Remember, though, that SQL is not a fully fledged programming language, so you should not try to write all of your business logic in your stored procedures. So let us look at how to create a stored procedure on DB2 on Cloud in SQL. First, you use the create procedure statement, specifying the name of the procedure and any parameters which it will take. In this example, the update_sal procedure will take an employee number and a rating which it will use to update an employee's salary by an amount depending on their rating. Then you declare the language you are using. You then enclose your procedural logic in the begin-end statements. In this case, giving employees who have a rating of 1 a 10% pay raise and all others a 5% pay raise. Notice that you can use the information passed to the procedure, the parameters, directly in your procedural logic. You can call stored procedures from your external applications or from dynamic SQL statements. To call the update_sal stored procedure that we just created, you use the call statement with the name of the stored procedure and pass the required parameters, in this case, the employee ID and the rating for that employee. In this video, you learned that stored procedures are a set of SQL statements that execute on the server. Stored procedures offer many benefits over sending SQL statements to the server. And you can use stored procedures in dynamic SQL statements and external applications. Welcome to ACID transactions. After watching this video, you will be able to explain what an ACID transaction is, give an example of an ACID transaction, and describe commits and rollbacks. A transaction is an indivisible unit of work. It can consist of one or more SQL statements, but to be considered successful, either all of those SQL statements must complete successfully, leaving the database in a new stable state, or none must complete, leaving the database as it was before the transaction began. For example, if you make a purchase using your bank card, many things must happen. The product must be added to your cart, your payment must be processed, your account must be debited the correct amount, and the store's account credited. And the inventory for that product must be reduced by the number purchased. Let us look at the example in more detail. If Rose buys boots for $200, then you can use an update statement to decrease her account balance, and another update statement to add $200 to the shoe shop balance, and a final update statement to decrease the stock level of boots at the shoe shop by 1. If any of these update statements fail, the whole transaction should fail to keep the data in a consistent state. The types of transactions in the example are called ACID transactions. ACID stands for atomic, all changes must be performed successfully or not at all. Consistent, data must be in a consistent state before and after the transaction. Isolated, no other process can change the data while the transaction is running. Durable, the changes made by the transaction must persist. To start an ACID transaction, use the command begin. In DB2 on Cloud, this command is implicit. Any commands you issue after that are part of the transaction until you issue either commit or roll back. If all the commands complete successfully, issue a commit command to save everything in the database to a consistent, stable state. If any of the commands fail, perhaps Rose's account does not have enough money to make the payment, you can issue a rollback command to undo all the changes and leave the database in its previously consistent, stable state. SQL statements can be called from languages like Java, C, R, and Python. This requires the use of database-specific access APIs, such as Java Database Connectivity, or JDBC for Java, or a specific database connector like IBM DB for Python. Most languages use the exec SQL commands to initiate a SQL command, including commit and rollback, as you can see in this example. Remember that begin is implicit. You do not need to call it out explicitly. Incorporating SQL commands into your application code gives you the opportunity to create error checking routines that in turn control whether the transaction is committed or rolled back. In this video, you learned that a transaction represents a complete unit of work, which can be one or more SQL statements. An ACID transaction is one where all the SQL statements must complete successfully or none at all. This ensures the database is always in a consistent state. ACID stands for atomic, consistent, isolated, durable. The SQL commands begin, commit, and rollback are used to manage ACID transactions. And SQL commands can be called from languages like C, R, and Python. Hello and welcome to Join Overview. After watching this video, you will be able to define the join operator, explain the role of primary keys and foreign keys in a join operation, and list the different types of join operators. A simple select statement retrieves data from one or more columns from a single table. The next level of complexity is retrieving data from two or more tables. This leads to multiple possibilities of how the result set can be generated. To combine data from two tables, you use the join operator. A join combines the rows from two or more tables based on a relationship between certain columns in these tables. In this simplified library database example, author and book are entities. This entity relationship diagram represents the relational data model for the author and book entity, as well as other entities such as borrower, loan, copy, and author list. The information is split into different tables. If you wanted to know which borrower has which copy of a book out on loan, you need to gather data from 3 tables: the borrower, loan, and copy tables. This is when you need to use the join operator. First, you need to identify the relationship between these tables, that is, the column or columns in each table to use as a link between the tables. In this entity relationship diagram, notice that the author ID, book ID, borrower ID, and copy ID have the primary key icon. A primary key uniquely identifies each row in a table. Notice also the entities on the lower half of the screen. Some attributes have FK in brackets next to them. This identifies a foreign key, which is a set of columns referring to a primary key of another entity. For example, the loan entity has the borrower ID attribute with the FK in brackets. In this example, the borrower ID attribute is the foreign key in the loan entity, which refers to the primary key for the borrower entity. So, if you wanted to know which borrower has a book out on loan, you need to gather data from the borrower and loan tables. You will need the borrower ID from both tables. Thus far, you have seen an example of combining 2 tables. But what if you need to combine data from 3 or more different tables? You simply add new tables to the joins. For example, if you want to know which borrowers have a book on loan and which copy of the book they have on loan, first you join the information from the borrower table and the loan table by matching borrower IDs. Then you join the information from the loan table and the copy table by matching the copy IDs. SQL offers you several different types of joins. You can extract a dataset corresponding to the intersection of the 2 tables involved, or you can choose a bigger dataset. You can go up to the point of selecting the combination of all the data from these 2 tables. The most common type of join is an inner join, which displays only the rows from 2 tables that have matching value in a common column, usually the primary key of one table that exists as a foreign key in the second table. There are also outer joins, which return matching rows and even the rows from one or the other table that don't match. There are many varieties of outer joins that you can use to refine your result set. In this video, you learned that you can use the join operator to combine rows from 2 or more tables. The tables being joined are related by a common column, which is usually the primary key of one table and appears as a foreign key in the other table. And there are 2 types of joins: inner joins and outer joins. Welcome to inner join. After watching this video, you will be able to describe inner joins, explain when to use an inner join, and describe the syntax of the inner join statement. A join operation combines the rows from 2 or more tables based on a relationship between certain columns in these tables. There are 2 types of table joins: inner joins and outer joins. The most common type of join is an inner join, which displays only the rows from 2 tables that have matching value in a common column, usually the primary key of one table that exists as a foreign key in the second table. This is an example of the syntax of the select statement for an inner join. Imagine you want to retrieve a list of all people who are borrowing books and the date of the loan. You need data from both the borrower table and the loan table. In the from clause, you specify the join between the borrower table and the loan table as borrower inner join loan. You identify the borrower table as B and the loan table as L. The table specified on the left of the join clause is known as the left table. In this case, the borrower table is the left table. For this join, you select borrower ID, last name, and country from the borrower table, and the borrower ID and the loan date from the loan table. In the ON clause, you specify the join predicate. In this case, the condition that the borrower ID in the borrower table is equal to the borrower ID in the loan table. Notice that in this join, each column name is prefixed with either the letter B or L. In SQL, this is referred to as an alias. Using an alias is much easier than rewriting the whole table name. The result set shows only the rows from both tables that have the same borrower ID. The borrower ID, last name, and country columns are taken from the borrower table and joined to the borrower ID and loan date columns from the loan table. The rows are displayed if the borrower ID matches. In this video, you learned that inner joins return only the rows from the tables that have matching value in a common column, usually the primary key of one table that exists as a foreign key in the second table. And rows from joined tables that do not have a matching value do not appear in the result. Welcome to outer join. After watching this video, you will be able to describe left outer joins, right outer joins, and full outer joins. Explain when to use each type of outer join, and describe the syntax of the outer join statement. Outer joins, unlike inner joins, return the rows from each table that have matching values in the join columns. Unlike inner joins, outer joins also return the rows that do not have a match between the tables. SQL offers you three types of outer joins: left outer join, right outer join, and full outer join. In a left outer join, all the rows from the first table on the left side of the join predicate are included, and only the matching rows from the second table on the right side of the join predicate. In this diagram, a left join matches all the rows from the left table and combines the information with the rows from the right table that match the criteria specified in the query. In this diagram, a right join matches all the rows from the right table and combines the information with rows from the left table that match the criteria specified in the query. A full join returns all rows from both the right table and the left table, so the full join can return a very large result set. In this diagram, the result set of a right join is all rows from both tables matching the criteria specified in the query, plus all non-matching rows from the right table. This is an example of the syntax of the select statement for a left join. In this example, the borrower table is the first table specified in the from clause of the select statement. So the borrower table is the left table and the loan table is the right table. In the from clause, borrower is listed on the left side of the join operator. Therefore, you will select all rows from the borrower table and combine them with the contents of the loan table based on the criteria specified in the query. In this example, the criteria is the borrower ID column. For a left outer join, simply called a left join, you will select the following columns from the borrower table: borrower ID, last name, and country. And you will also select the following columns from the loan table: borrower ID and loan date. The left join selects each borrower ID in the borrower table and displays the loan date from the loan table. The result set shows each borrower ID from the borrower table and the loan date for that borrower. There is no loan date for the last three rows, so the borrower ID and the loan date show null values. This is an example of the syntax of the select statement for a right join. In this example, the borrower table is the first table specified in the from clause of the select statement, so the borrower table is the left table and the loan table is the right table. In the from clause, the loan table is listed on the right side of the join operator. Therefore, you will select all rows from the loan table and combine them with the contents of the borrower table based on the criteria specified in the query. In this example, the criteria is the borrower ID column. For a right join, you will select the following columns from the loan table: borrower ID and loan date. And you will also select the following columns from the borrower table: borrower ID, last name, and country where the borrower ID in the loan table matches the borrower ID in the borrower table. The result set shows each borrower ID from the loan table and the loan date for the borrower, where the borrower ID in the loan table also exists in the borrower table. For the last row, there is no matching row in the borrower table, so the borrower ID, last name, and country show null values. This could indicate a problem for the library. It indicates there is a book on loan to an unknown person. This is the syntax of the select statement for a full join. For a full join, you select all rows from the borrower table and all rows from the loan table. The result set shows all 8 records from the borrower table listed with the corresponding data from the loan table. Once again, 3 rows return a null value because borrowers Peters, Lee, and Wong have never taken a book out on loan. The last row returns values for borrower ID and loan date from the loan table, but returns nulls from the borrower table. In this instance, there is no match in the borrower table. The borrower of this book is unknown. In this video, you learned that there are many varieties of outer join that you can use to refine your result set. Left outer joins return all rows from the left table and all the rows from the right table that match what an inner join would return, and all the rows in the first table that do not have a match in the second table. Righter outer joins return all the rows that an inner join would return and all the rows in the second table that do not have a match in the first table. Full outer joins return all matching rows from both tables and all the rows from both tables that don't have a match.